Hello, everyone. We are going to conduct our lab on restoring forces and harmonic motion online completely, but it's going to be split into 4 teams data. First of all, I'm going to do a review on springs. Then we're going to do the first part of the lab, which is finding the spring constants. Then we'll use the spring constant to determine what is the period of an object moving on a spring. Let's start. If we have a spring connected to a mass with spring constant K, the motion of the spring is, in this case, in the x direction. And obviously, the restoring force is opposite the direction of the motion. Hence, we can write that F is equal to minus K times x in the I hat direction, where that's my x direction. We're going to now change perspective a little bit by hanging that mass. Now this is my mass, this is my spring constant, and I'm going to hang multiple masses and just measure, but now since I'm hanging it, I can draw a free body diagram, where obviously this is the spring force, and this is W, which equals to mg. We can use this method in order to find the spring constant, because if our massless spring would be hanging with nothing on it, the extension right here is going to be my extension y. And I'll just call it delta y here, because that's the extension from 0. And I can then measure what the spring constant is by graphing. The graph would look this way. And G in this direction. And this will be the delta y's in this direction. And I'll have just dots, dots, dots that I will then put onto a computer, either in Logger Pro or in Excel, put those few dots. And obviously the slope will be equal to the spring constant in newtons per meter. Let me do that. And what I'm going to do is I'm going to do now 4 different springs. And for each spring, I'll give you the data. I'll measure and give you the data. Notice, I'm going to be measuring the distance from the floor. It's on you to find the delta y's. I'll help you out with this. So, notice what I have right here. Here's the spring hanging above the floor. And I'm going to measure the distance from the floor as I add more and more masses onto that spring. I'll do about 5 masses for each spring. I'm always measuring to the same exact part of the spring. In this case, it's going to be this little thingy at the very bottom. Little thingy means the hook at the very bottom. So what I'm gonna do for you is I'm gonna actually give you the numbers. And the number right here for the first number is 48.1. 48.1 is my original number. Next, I'm hanging 100 grams This is the blue spring, and group number 1 will have the blue spring. Lab number 1 will have the blue spring, and this is ending up again from the bottom of the hook of the spring, and that's 46.1. Obviously, your delta Y will be the 48 point something minus that. Okay. Now I'm going to do 200 grams. This ends up being 42.7. I'm going to add the 200 grams at the bottom so that it will make 300. Uh-oh, that's not very good. We will have to do this a little bit better. I had a little bit too much of a torque, sorry about that. Now I have 300 grams. That ends up being 39.4. I'm now going to do 400 grams. And I can hang it this way. That's going to be 36.3. And the last number is going to be 500 grams that I hang. And that's going to be 33.0. Now, please do not include the 00 in your data. Only the delta Y's, the changes from the 00 is what you should include in the data. Now we're going to do a different spring. Next spring is the yellow spring. For the yellow spring, let us start with the original location. Original location, you may see the 70, so it's a little less than 70. And to be more precise, this is going to be 68.4 at the bottom of the hook. Let me redo that. Let me redo the 0, thing, because I changed something at the top. We said 68.4, it's actually 68.8. So change it to 68.8. Now I'm hanging 100 grams. Ends up this is now 66.9. $200 grams. And that ends up being 64.0. 300 grams. Notice that this is a little stiffer spring, hence the extensions are not as big. Okay, 300 grams, and I'm at 61.1. I'll go next to 500 grams. Notice I didn't go to 400 this time, but 500 grams. And we're down to 55.4. And 600 grams. And this is down to 50.0. Done with spring number 2. Spring number 3 is a way softer spring. Since it's a way softer spring, you don't even see it until I tilt the camera just a tad high. Now you can see it. As a result, I'm going to hang masses that are not as large. For spring number 3, which is for breakout room number 3, we're going to start with a mass of 20 grams. But first of all, let's find the bottom of the hook right there. Kind of tough to make it relax. Relax, baby. And that's the location right there is 91.7. I'm hanging at 20 grams here. And it's all the way down to 84.2. Now I'm hanging 30 grams. And it's down to 80.3. Next is the 40 gram. Goes to 77.2. Now I'm going to hang a whole 100 gram. And that goes all the way down to 54, sorry, 53.7. We're down to spring number 4. Spring number 4, for breakout room number 4, is this bronze color spring that you've seen right here. Its top location is at 74.2 centimeters. I'm starting by hanging 100 gram mass, and it's down to 70.2. I'll hang 130 . And it's down to 69.1. Next, I'm hanging 200. And it's down to 66.6. Next, I'm doing 230. And it's down to 65.2. Last I'm doing 400. And it's down to 59.1. That concludes the first part of measuring spring constant. Now, let us do the second part of this lab, which has to do with period of a harmonic oscillator. Let's go back to our definition right here. And let's look what happens not when this mass is hanging still, but rather what happens when the mass is going up and down, which will be the equivalent of what happens when the mass is moving to the right and left. So now, rather than being pulled, you pull the spring over equilibrium, it will run this way, then it will compress the spring, and that would make it push this way, back, forth, back, forth. If you look at position versus time, you're going to get, if I just started it at a certain location, you're going to get a sine wave. For that part in the lab, we will use motion detectors. We will use the motion detectors for, of course, each and every spring. Our spring constant is what we found in the first part. Now let's see what the period is. If we're looking at x in some amplitude times either a sine or cosine wave, I'll use a sine. That's a solution to our equation, because the equation is actually this. Minus k times x I hat, that's equal to the mass times the acceleration I hat, which I can write as minus kx equals to mass times the derivative with respect to time, pardon this in the middle, derivative with respect to time of x itself. I hats canceled out. That's my actual equation. The equation goes as follows. X is equal to m over k times the second derivative with respect to time of x itself. With one little caveat, there is a minus sign right there, so let me move this minus right here. And take a function of something, same thing twice, and good answer to that would be x equals sine wt plus phi. Take the first derivative of that, and you're going to see that dx dt is going to be equal to wa sine wt plus phi. Sorry, cosine. The derivative of sine is cosine. Take a derivative of a cosine. Let me move the camera just a tad lower. Take a derivative of cosine. And that's minus sine. But you also pull another w, so it's minus w squared times a times sine of wt plus phi. But guys, that fella, that's the original x. So it's equal to minus w squared times x. Therefore, my equation for position versus, the equation, Newton's second law here, minus kx is ma, yields this equation right here, which means if you want this to be correct, then w squared will have to be equal to K over M. Notice that this is actually on the opposite side. You have to multiply by K, divide by M in order to have that in this direction, or W itself is going to be equal to square root of K over M. But W right here is equal to 2 pi divided by the period. You've done that in physics 1, physics 2 AG, 2 AG or something. So I write the period, therefore, is going to be equal to 2 pi square root mass over spring constant. That's my hypothesis for part 2. So now we're going to start part 2 right here. What I'm going to do is for part 2, I'm going to connect a motion detector. And the motion detector should get the position versus time for your 3 springs. Just setting it up. So now what I'm doing is, as you can see, I'm going to aim this at spring number 1. The spring number 1 will now have the motion detector directly underneath it, and a mass that will be hanging that will be somewhat similar to the masses we used for finding out the spring constant. One little thing about those masses, notice that rather than having the side that's slotted here, I'm going to use the other side right there towards the motion detector. So this side will aim towards the motion detector so that I get the most reflection and get nice curve on a motion detector. Now, same as in the pendulum problem, I don't need much of a motion, and I want to make sure that we're directly above the motion detector. That's what I'm doing right now, checking that we're directly above the motion detector. Connect it to the correct location, which means connect it to the interface, connect it to computer, and I'll show you the results in a moment. For now, though, I'll start it on a move. I guess it's kind of moving in a weird way, so I'm going to straighten it up a little bit. I'm going to also move the screen in such a way that it will be fairly easy to see the screen. You hear the clicks. And let me make sure that you're seeing this thing still moving. And now I'm gonna move it so that you can see the screen. And rather than you getting to try and see the screen itself, what I'm gonna do is I'm gonna say, all I have to do here is auto scale. And save as. I'll write down here breakout room 2 or breakout room 1. And that's it. I'll send it to you. You will figure out how to find out the period for this particular spring. Next, I'm going to change that blue string to yellow string. You can use the half. Move it a tad. And down. Measurement taken. Notice that the graph for the position versus time looks to be a little bit higher. That's just because we were further from the detector. I can still do some sort of auto scale. And I'm going to save it as breakout room 2. That's going to be given to team number 3. Sorry, number 2, breakout room 2. Now we're going to break out room 3. That will be a tad trickier because that's a very, very soft spring. So I'm going to use something that's a little bit longer, and I hope it will work with this. Main problem here is that we need a little bit of a reflection. It's not that easy to get a reflection on this. Ah, 200 grams, maybe a little bit too much. So let me actually raise the whole thing a little bit up. Okay, breakout room number 3. As you can see, the period in this one is a bit longer. Oh, I just messed it up. I just messed it up a little bit because this became breakout room number 3. So Let me do this safe again. I may need to do breakout room 2 again. I'm going to do breakout room 2 again. So again, guys, it's important to see what mass you use. And for the, remember for the spring number 1, it was 500 grams. For spring number 2, it was 500 grams. For spring number 3, it was 200 grams. I'm doing number 2 again. And now I'm going to do the very last spring, and that's the spring for breakout room. Number 4. And again, I'm using 500 grams for this spring. And ladies and gentlemen, we are done.